Okay, picking up with the second half of our antiderivative lesson 23, we actually have another definition that we can write here, which is an equation that contains a derivative of a function. Is called a differential equation. Bet you've heard of those. And that is exactly what a differential equation is. It's just an equation, so it's got an equal sign, two sides, and somewhere in that equation, maybe more than one place, there is a derivative. So a good example would be from number 8, the example we finished on the last video. You notice how it says g prime of x equals, and then there's some other stuff. That is an equation, and it contains a derivative because it's g prime of x. So yes, there is an entire math class devoted to solving differential equations, which we often call diff-EQ. You need a little bit more calculus though first. So if it is in your future, it's a couple semesters down the road, but something to look forward to. If we start our process of talking about what differential equation solutions are, okay, what does it mean to have solved it? What does it mean if I look at this equation and I say, I have solved that equation? Well, it really means that I've found a g function that makes this true. This is a solution to this. Okay? So the solution to a differential equation is a family of functions that makes the equation true. It's a family of functions because we know, as we discussed in the last video, that there's an infinite number of those functions that will actually be true, have that derivative, right? So the general solution will include the arbitrary constant, that plus c that we've just been talking about. So the arbitrary constant c to denote the family of functions. So we can't list them all out. So we just add the plus c as a way to say, this is the family. It's all of those sine x's plus anything you could add to it. That's a constant. Okay. However, you can find a particular solution, one member of that family. Okay. So a particular solution is one member of that family of functions. And it's going to be determined by a point. A specific point on its curve. And we call that an initial condition. So we are kind of defining this word initial condition in this discussion. Let me go back to this picture over here. So these are, because we said before, these are not all of the members of the family, but these are some members of the family of functions that are basically solutions to f prime of x equals cosine x. And so generally we would have said that the solution would be y equals sine x plus c. But if I said the initial condition, that I want the particular solution that has the point 0, -2, there's only one member of the family that will have that point. So that gives you that one particular solution to your differential equation. Okay. So let's do a fresh example or two. First one, we're going to find f of x if f prime of x, so here's our differential equation. Here's what the derivative is equal to, and here is an initial condition. So I see my derivative. I'm going to go ahead and find the particular solution, the general solution, by figuring out the function. So I might want to think of that as 2x minus 3x to the negative 4, so that when I go to add 1 and then divide by that number, it's a little easier to do. Clean that up just a little. So I have x squared. Let's see, a negative divided by a negative is a positive. Looks like the 3's will cancel too. So I have an x squared plus 1 over x cubed plus c. So that's my general family. All of those functions will be solutions to that differential equation. But if I want the one that has this 0.13 on it, then I'm going to plug in 3 for the y and 1 for the x and solve for c. Oh, I didn't really plug in the 1 there, did I? I mean, I half did. It was a feeble attempt. All right, there we go. 1 squared plus 1 over 1 cubed. It's a lot of 1's. 1 plus 1. So I've got 2 plus c. So it looks like c must be another 1. Great. So I can say my particular solution, where am I going to write that? I'll go up over here, would be that f of x equals x squared plus 1 over x cubed plus 1. Now this is the particular solution that includes the initial condition. For the second example, we're going to do the same thing, but we've got to do it twice. This notation got a little screwed up right here. This is supposed to say f double prime of x equals, and then here's the equation. So this is still a differential equation. It has a second derivative in it, but that's still a derivative. So it still qualifies as a differential equation. So we're actually going to have to do this twice because we want to find the original function and we have the second derivative. So we're going to take the antiderivative once, since that'll give us f prime. We'll use the initial condition that's given to us for f prime, and then we'll do it again. So going from f double prime to f prime will be take an antiderivative. So I have 4x minus 2x squared minus 10x to the 4th plus c for my first derivative. I'm going to plug in 0 for the x and 1 for the y. Oh, that gives me a pretty straightforward. So I now have my full first derivative. And we'll just go ahead and do this problem or process again. So to get the function, I'm now going to take an antiderivative of its derivative. So just applying mostly the x to the n antiderivative rule. Of course, I'm going to run out of space. So I have 2x squared minus 2/3 x cubed minus 2x to the 5th plus x plus c. No, I don't. I realize I did something wrong right here, which I should have stopped myself back there, but I didn't. Let's see, when I did 6x and I did x to the second power, I should have divided by 2 and not 3. So that would have given me 3x squared here. Wouldn't have changed my c. I'm just fixing all those places. I think it's right there. Okay. Let me go back and make sure we got that right now. So I should have put a 2 down here. When I did x squared, then it's the 2 that goes down there. And then 6 divided by 2 is 3. I plugged in x equals 0, so it wouldn't have changed my c. So I would have ended up with just a minus 3x squared instead of a minus 2x squared. That matters that when I did this, these 3's would cancel. So I would have had just a minus x cubed. Oh, goodness gracious. Okay, I think we're okay, back on track. So now we're going to use the f of 0 equals 2. Oh, and just get that same easy, 0, 0, 0, 0, and c. So my final answer, which once again, I don't have enough space for, would be 2x squared minus x cubed minus 2x to the 5th plus x plus 2. Okay. So number 3 is actually almost the same problem. It's just given to us in the context of velocity and acceleration and so forth. So we have a particle that's moving in a line, and we have its accelerations function. They give us an initial velocity and initial position. And so you need to find the position function. We're doing this exactly the same way that we just did the last problem. You're going to go from acceleration to velocity using an antiderivative. Use your initial condition for velocity to find the particular velocity function, and then do it one more time. Use an antiderivative to get to position and plug in your initial condition. So I want you to pause the video and give that a try, and then come back and check your answer. So hit pause now. Okay, check your work. I went ahead and took an antiderivative of 6t plus 4 here, added my plus c, and then plugged in 0 for t, so these are gone. It's just a c on the right side, and -6 for the velocity. So that gave me a velocity function that I then took the antiderivative again and used the s of 0 equals 9 to plug in 0 for the t. All 3 of these go away again. I'm left with just c on the right side. And so c is 9, and there's my final position function.